Testing, mic check, testing. Mic check, testing, testing. Just trying to get a test of the audio. Testing, testing. Woo. Sorry about that. Just trying to get a test of the audio. Alrighty, we are ready to go. Hello, everyone. Welcome back to another episode of Conquering Physics. We are on our ninth installment. And today's problem is working out a rotating disc. And so for the setup, we have a disc of mass M. Disc of mass M. And radius R is rotating at angular velocity omega naught. And another disk of mass m and radius little r is dropped on top of it. So it has the same mass, but it's a little r, such that the centers coincide, so they're dropped right on top of each other. Smack dab in the middle. And it says that both disks now spin with angular velocity just omega. This is a new one. So this is the initial, this is the final omega. What is omega? Okay, so here's what's interesting is I think we have to make a few assumptions in this problem. I think we basically assume this is spinning frictionless and it won't stop. And once you drop this disk on it, it will then pick up angular velocity in itself, and so at total we have to have a conservation of angular momentum in the system. So those are our assumptions. So just like momentum, conservation of momentum of initial and final, there's also a conservation of angular momentum. Okay, and so for this, the moment that we need to take into consideration, well, basically we need to calculate the moment. And so the moment, as we had discussed before, but this is equal to I r squared times dm. So let's maybe check this really quick. Yeah, so it seems that it doesn't tell us anything about. Pardon me. It doesn't tell us anything about what kind of angular or moment we have, like the distribution. Okay, what is omega? Okay, yeah. So I just got to think about this real quick. Yes, I think this problem might end up being easier to solve than I think, but I haven't learned the quick techniques, and I'll probably end up going over them sometime later. But for now, let's try to just work all this out by hand. So we know that this has mass m, and this is rotating in such a way, right? And so our angular momentum for the system is going to be moment times omega. And so I don't remember what the notation is for angular momentum. Let me see. Oh, okay, it's L. Angular momentum L is equal to the moment times omega. And so this quantity has to be conserved. Okay, and so if we have a uniform mass density on this, the density of this is going to be equal to big M divided by area. And so that would be 4 pi r squared. 4 pi big R squared. And so if we were to solve this equation, this is going to be equal to a double integral for the area, because this is the density of this, and dm turns into the area, the equation for the area times okay, it's the integral for density times dA, which is the area. And so this, yeah, sorry if I'm a little delayed. I'm trying to think because I haven't tackled these problems in a while. So we know that dA in this case could actually be calculated as a function of dr times the radio component. And so we could actually turn this area into a double integral, integrating from 0 to 2 pi, and then 0 to big R. And so this dA component, since we're turning it into polar coordinates, it's going to be r d theta, or d phi, however you want to define it. And so this is a constant, so we can move it out. And remember, rho is equal to m times this. We'll leave it rho for now, just to make the calculation easier. When we calculate this r part, so we could actually calculate this theta part first, and we'll get a 2 pi out. So we'll calculate the r part first. I don't want to get ahead of ourselves, but we do eventually want to be able to calculate these things a bit faster. And so this r part, we get r cubed, and so the integral of r cubed is r to the 4th divided by 4. We evaluate from 0 to r, and so we get big R to the 4th divided by 4. And so now we integrate from 0 to 2 pi of this part, and this is a constant, we could pull it out. And so when we evaluate this, we get theta evaluated from 2 pi to 0, which gives us just 2 pi. And so this is what this initial I is. So the thing is, once we drop this other M, this other disk onto it, we're going to need to see how does this change. And so what this is going to change is going to be our I is going to change, and so will our omega. And so if this is our initial, then we have a final. And initial is equal to our final. And so what we want to solve for is this omega. So this I initial that we're calculating, this is the initial one. We calculated times omega naught, and what we want to solve for is this. And the way we solve for it is by solving for each of these components. We just solved for the moment, the initial moment of inertia. And so now we want to solve for the moment of inertia for the second part. And so the second part, it's actually going to be this first initial part plus the moment of inertia for the second part. And so if we were to actually kind of extrapolate out what we got for the first one, we can notice that we could apply a very similar principle to this one, except this density is going to be a little different, and instead of a big R, we're integrating to a smaller R. So let's first work this one out. And so this density, as we recall, is equal to big M 4 pi R squared, big R to the fourth, 4 2 pi. So this 4 times 4 is 16, and 2 is going to give us 1/8. We can get rid of these two. We're left with 2. And so we have M R squared. This pi cancels out. This divided by 8. Because 2 over 16 gives us 1 over 8. And so, very similar to the second disk, we could make a quick approximation that it's going to be the same value, except this R is actually little r instead of this big R. So the additional, so we'll say that IF is equal to the big disk plus the little disk, and the moment of the big disk is this one plus the little disk, LD for the little disk, is going to be equal to something similar. So the integration is the same. All we would replace is for the density, we change this big R to little r, and to this, we change this big R again to the little r, but it's this little r. We'll denote the little RO. And so this is going to be the, so just to avoid doing the calculation, we know it's going to be proportional in this fashion. And so when we work this out, we have big M R squared over 8 omega naught divided by, and remember this part is going to be this plus this. Big M R squared over 8 plus big M R squared, little r squared. Over 8. So we can multiply top and bottom by 8, get rid of those. We get rid of these m's, and what we're left with is r squared over r squared plus r squared omega naught. And let's see, what are our options? So our options are A, r squared omega naught over big R squared, little r squared. B, big R squared, big R squared, plus little r squared omega naught. C, big R squared plus little r squared over r squared omega naught. D, big R squared plus little r squared over big R squared omega naught. E, omega naught. And so from what we got right here, we can see that it is B. And so just to kind of play around with our intuition, let's assume that little r, so this is kind of just an added little bit. I think it's important to kind of to see this whenever you're dealing with this stuff and kind of get a sanity check. If we were to get a whole entire disk that was the same size as this, you could imagine if you had this spinning with a certain angular velocity, and let's say that this r was the same size as this, you could imagine that somehow they would distribute, I guess, their spinning type angular velocity equally, right? and so they would this new combined um, angular frequency, angular velocity would be, or angular frequency would be about the same. I mean, one half of it, right? And that makes sense, right? If you have r squared over r squared plus r squared, then this is one half of the original angular frequency. Yeah, and so one way we could just look at it is if we were to have I omega not spinning, right? If we multiply this by 2, by basically adding a whole nother element of itself to it, then we know that this would have to be divided by a half. That's a quick sanity check just to make sure that, okay, this actually makes sense if we try to think of it using our intuition and setting these equal to each other. I hope that was insightful, and sorry about the coughing and the delay. I'll make sure to crispen all that up on the next one. Until then, y'all take care. Bye bye.